Hello viewers, welcome back to my channel. If you are new to this channel, hit on the subscription button and turn on the notification bell so that you can be well informed whenever a new video is released. For our old subscribers, thank you for staying tuned. Today, we are going to be looking at mechanics, and the topic of discussion is conservative feeds. What are conservative feeds? What do we mean by conservative feeds? Or when is a feed said to be conservative? For us to have a better understanding of this topic, we must understand the rule of differentiation, the basic principles of differentiation, and how to differentiate different functions so that we can have a better understanding of this topic. Let's revise our knowledge on the basic rules of differentiation. We all know that if a function y is defined as x to the power of n, y equals x to the power of what? N. From the what principle of differentiation, it simply means if I want to differentiate y with respect to x, also termed as dy over dx, is given as, for the rule of differentiation, anytime I'm differentiating, it means that power should come down. The power on the what on that variable is going to what come down, so that we are going to have n x raised to power, then now remove 1 from the power. Remove 1 from the power, so n minus 1. This is the basic rule of differentiation. This is the basic rule of differentiation. So that means dy dx equals nx raised to power n minus 1. This can also be written as what? Y prime, to show that I am differentiating once with respect to x, equals n x raised to power n minus 1. This is the basic rule of differentiation. So let's look at this. If you are to differentiate, if y equals x raised to power 4, if y equals x to the power of 4, it simply means that dy dx, that is, out if I'm to differentiate y with respect to x, I'm going to have, using that same principle, the power should come down, 4 multiplying x. Then what happens to what? To the power. We take away 1 from the word power. It means what? 4 minus 1. This will give us 4 times x. 4x into what? 4 minus 1 gives us what? 3. This is the rule of differentiation. Also, if y is defined as, let's say, 2x to the power of 7. If y is defined as 2x to the power of 7, dy dx will be given as, don't forget the rule, the power should what? Come down. The power is coming down, multiplying what is on ground before. I'm adding 2. Multiplying x is for what? 7 minus 1. This will give us dy dx to be equal to 7 times 2 will give us 14. 14 raised to 14x to the power of what? 7 minus 1 gives 6. This is how we differentiate a simple function. For the first one, number 1, I want to, if y is defined as what? 2k squared t, or let's say 2k squared. 2k squared. Dy the what? Here, I can never have dy dx because I don't have any what? Any function of x here. If I want to find dy dx, the result will be what? 0. Why? I don't have x here. What I can add here is what? Dy over what? Dk. I want to differentiate y with respect to k. Dy dk will give us, don't forget, using that same principle, 2 should come down. 2 multiplying another 2 with what? K is for what? 2 minus 1. This will give us what? 4k. 2 minus 1 gives us what? 1. So we have what? 4k. So dy dk equals what? 4k. But using the same function, if I want to find dy dx, using this same function, if y equals 2k squared, If I want to find dy dx, look at that function very well. Do you see anything in terms of x there? No. Since there is no term in terms of x in this function, it means anytime I want to differentiate y with respect to x in this type of function, the result is what? 0. Because the whole of this is not as if it's what is ordinarily what? Constant. It is not as if it is what? Constant. So dy dx will be equal to what? 0. The only result you can have is what? Dy dk, because it is only y and k that are visible, that we can see in that function. So these are the basic rules of differentiation. So we are not going to be using this idea to understand the concept of conservative what? Field. Now, what is a conservative field? A conservative field is a field in which the total work done is 0. A conservative field is a field in which the total work done along the what? A circular path is 0. That is, what are we trying to say? What are we trying to say? For us to understand this better, we can express conservative field mathematically as what? A field that occurs whenever call f equals 0. Is a field that occurs whenever call f equals what? 0. So a conservative force field is when the call of f is defined as 0. How do we interpret this? This simply means that the call of that force, which is expressed as the determinants, don't forget this is I, J, and what? K. The first one, d dx, d dy, d dz. d dz of the force in the direction of x, the force in the direction of y, and differentiating the force in the direction of what? Z. So this is how we define our what? Determinants. Where this first one is positive, negative, and positive. That is plus, minus, and plus. So this is how we define the call of a function f in the Cartesian coordinates x, y, and z. For us to understand this better, let's look at one or two examples. This simply means that we are going to use our knowledge of differentiation to evaluate these determinants. And once we finish evaluating this and the result is 0, then it means that that field is conservative. But whenever the call is not equal to 0, it means that the field is no more what? Conservative. What are you trying to say? Let's look at one or two examples. Example 1. Show whether or not the following fields are conservative. Show whether or not the following fields are conservative. Number 1, when we have y in the direction of I plus x minus y in the direction of j. Y in the direction of I plus x minus y in the direction of what? J. So how do we show that this function is what? Is a conservative force or a conservative field? From definition, for it to be conservative, it implies that the call of this function must be equal to 0. That is, call of that what? Function f should be equal to what? 0. Where f is defined as the whole of this. So that the call of f, which is now defined as this I, j, and k of d dx, d dy, and d dz. So let's just start. For I, what is the coefficient of I in this function? The coefficient of I is what? Y. Coefficient of I is what? Y. d dy. Okay, for j, what is the coefficient of j? The coefficient of j is what? X minus y. What for k? Do you have any function in terms of k here? No, it means what? Is 0. So let's now evaluate this. This will give us, for us to what? Evaluate this determinant for I. Don't forget this is plus, minus, and plus. For I, for me to what? Evaluate I, I'm going to what? Close the row of I and also close the column of I. This is I, close the row of I, cover everything, and also cover the column of I. What is left? This. By closing the row and also what? Closing the column. Close the row and also what? Close the column. So we are left with what? D dy, d dz, then x minus y with what? 0. So in that case, I'm going to what? Something like what? Cross multiplication, because this is what is left. This will go for this, and also this will go for what? This. So that d dy of what? Of 0. By differentiate 0 with respect to what? Y. My answer is what? 0. Minus this for the second one. By differentiate this function with respect to what? Z. Is there any function in terms of Z here? No. It also means what? 0. That's what for I. For J, don't forget, J always comes with what? Natural negative. So for J, so I'm going to do the same thing for J. Close the whole of J, also close the column of J. The whole of J and what? And the column of J. Let me clean this. So let me close the whole of J and also the column of what? J. This is what? The whole of J, and this is what? Column of J. What are we left with? This. Can you see it? So we are left with what? D dx, D dz, y, and 0. By closing the what? The whole and the column. So I'm left with, so don't forget, close this and also what? Close this. D dx of 0. Don't forget, this will go for this. This will also what? Go for this. Differentiate this function with respect to what? X. This will give us what? 0 minus the natural minus. For the second one, don't forget, we are going to what? Differentiate this function with respect to what? Z. We also give us what? Z. Y. Since this is Y, not Z. I'm going to have what? 0. That's what? For J. Plus, minus, then the last one, plus K. Let's see what we have in terms of what? K. Using the same principle. Close the row, also close the what? Column. This is the what? Column for K. This is what? Row for K. What are we left with? D dx, D dy, y, and x minus y. Can you see that? So I've closed the row and also must close the what? Column. So that this will go for this minus this should go for this. So differentiating this function with respect to what? X. It simply means that it is only x I want to differentiate. Any other thing that is not in terms of x should be what? 0. Anytime I differentiate the constant, it's always what? 0. Differentiate this function with respect to what? X. So this one is like s raised to power 1. If I differentiate s raised to power 1, the rule is that what? That one should come down. I'm going to have 1 multiplying x raised to power what? 1 minus 1. So that 1x raised to power 0 and x raised to power 0 is the same thing as what? 1. X raised to power 0 is the same thing as what? 1. So this will give us what? 1. This will give us what? 1. So for the second one, I want to differentiate this function with respect to what? Y. I want to differentiate this function, don't forget, for K. Close this and also what? Close this. I want to differentiate this function with respect to what? Y. This will give us what? 1. Because this will give us 1. So I'm having what? 1 minus 1. So at the end of the day, I'm going to have 0 minus 0 times j, 0 plus 1 minus 1 is 0, 0 times k, 0, which is give us what? 0. So it implies that what? The call of that function equals 0. Since the call of the function is equal to 0, it shows that that field is a conservative field. Since the call of the function given to us is 0, this shows that that field is a conservative field. It shows that that field is a what? Conservative field. Let's look at another example. Still on conservative field. Let's see another example. Example 2. Still on what? Conservative field. Still on conservative field. The second example. Show whether or not the function number 2 f, which is defined as 2x sine 2y minus 3y squared. All this into I plus open bracket 2 minus 6xy plus 2x squared plus 2x squared cos 2y in the direction of what? J. So show whether or not this function is a conservative field. Show whether or not this function is a what? Conservative field. The first thing we need to do is to what? To define our what? Conservative field as what? The determinant. Don't forget this is what? I, J, and K. The determinant of the coefficient of I. That is this the s, isn't it? This is what? D dy. This is what? D dz. D the what? Dz. This is z. The coefficient of what? I, which is the whole of this. I'm having 2x sine into 2y minus 3y squared. That's the coefficient of what? I. For j, I'm having 2 minus 6xy plus 2x squared plus 2x squared cos 2y. Cos 2y. This was for j, and for the other one we have what? 0. So these are my what? Determinants. So that if I now do what? Solve for my curve of that function f. So let me start with I. Still on the same principle. Close 0. Also what? Close is what? Column. Close the goal of I. Close the column of I. So if I close the row of I and also what? Close the column of what? Of I close this. So I'll be left with what? This with 0, isn't it? Close the row, close this, the whole of this, I want to close this, and also what? I want to close this. So have you seen that? So I'll be left with what? D dy of 0 and d dz with what? 2 minus 6xy plus 2x squared cos 2y. So d dy of 0 will still give me what? 0. So I'm going to have for I 0 minus, for I 0 minus, don't forget, it's still like this. D dy of 0 is what? Is 0 minus the result of this. You can check this function, the whole of this function will tell to what? Z. Check this function. Is there anything like Z here? No, there is nothing like Z. It means the result is also what? 0. That's for I. This is plus, minus, and plus. So plus, the next one is what? J is always comes with what? Minus. Into, for me to get J, close the row, also close the what? Column of J. Close the row, also what? Close the column of what? J. This is J. Look at it. So I'm closing the row, I'm also what? Closing the column. So what are we going to be left with? We are left with d ds of 0 and d dz of 2x sine 2y minus 3y squared. So d dx of 0, differentiate this function, we tell it to what? X. We also give us 0 minus, differentiating the whole of this function, we tell it to what? Z. Is there anything like Z here? No, there is no function or there is no terms in terms of Z. So it also means what? This is also what? 0. That's what? I and what? J. For the last one, plus K into, so let's work on what? Our K. For K, close the what? Row, also close the what? Column. Close the row, also close the what? Column. What are we going to be left with? Differentiate this function with respect to what? X. Also, differentiate this function with respect to what? Y. By differentiate this function with respect to what? X. What am I going to have? And it means what? It's only X. I want to what? Differentiate. Anything that is not in terms of X, I'm going to what? Negate it. Let's start. I want to differentiate the whole of this function with respect to what? X. Let me start with the first one. This 2 is the what? Is a constant. Does it have X? No. This is what? 0. This is what? 0. Let me solve it here first. Minus the second one here. We set it to X. It's only X I want to differentiate. By differentiate X, I'm going to have what? 1. So I'm going to have minus 6. It remains 6y. It remains what? 6y. Out of this, plus, by differentiating 2x squared, we subtract to x. That 2 is coming down, making it what? 4x. What comes to this? 4x cos what? Cos 2y. 4x cos what? Cos 2y. 4x cos what? 2y. We turn to what? X. So this is what we're going to have. So the whole of this minus the second one now. How to differentiate this function? We turn to what? Don't forget we are in what? We are in K. And K is like this. Close the column, also close the what? Row. So I want to differentiate this function. I want to differentiate what? This function. We started to x. I've done that. Minus differentiating this function. We started to what? Y. I want to differentiate this function. We started to what? Y. If I do that, it means it's only y I want to what? Differentiate. Any other thing, they remain the way they what? The way they are. I'm going to have. If I differentiate the sign, I'm going to have cos. If I differentiate cos, I will have negative sign. If I differentiate sign anything, I'm going to have what? Cos that thing multiplied by the derivative of that thing. If I differentiate sine 2y, I'm going to have what? Cos 2y. So I'm going to have 2x cos 2y multiplied by the derivative of what? 2y. We said to what? Y. I'm going to have what? 2. So that 2 multiplying this 2, making it what? 4. 4 cos what? 4x cos 2y minus what? Let's look at this. If I differentiate what? This, we said to what? Y. I'm going to have what? 2 times 3, 6y minus 6y. So the whole of my k is now this. So if I open up this bracket, I'm going to have, let's look at it. Let's look at it. This is plus 4s, this is minus 4s. So this can what? Cancel. Plus 4s has cancelled what? Minus 4x. Now 4 is what? Cos 2y. Plus 4 is what? Cos 2y. So they are what? They are gone. So my plus 4s cos 2y has cancelled minus 4s cos 2y. Again, minus and minus, making it what? Plus. Plus 6y that is there has cancelled what? Minus 6y. Can you see that? Minus turns to plus. Plus 6y has cancelled what? Minus 6y. So at the end of the day, I'm adding what? 0. I'm adding what? 0 for what? For k. Because 0 minus 0 will still give us what? 0. At the end of the day, the call of that function is what? Giving us 0. This shows that the force field f equals 2x sine 2y minus 3y squared I plus 2 minus 6xy plus 2x squared cos 2y is a conservative force field. Is a what? Conservative force field. The next thing we are going to be looking at is the work done in strings. Work done in strings. How do we evaluate the work done in a string? We know that from work done in string is expressed as half ks squared. Half k what? S squared, which is also the same thing as the kinetic energy of that string. The work done in a string is defined as half ks squared, which is also the same thing as what? The kinetic energy in what? In that string, which is also the same thing as what? Half fe or fx, which is the same thing as what? Half what? Fx. Either we find it in terms of what? The spring constant or the string constant k, or we find it in terms of the what? Force. X is the what? Extension. S is what? The extension in that what? String. It can be in terms of what? Compression. So that if we evaluate this, we can still write this as work done to be equal to half ks squared, which is known as what? Kinetic energy half mv squared. So this is the work done in a string. If you have to look for what work done in a string, this is the formula we use to calculate the work done in a string. K is the spring or string constant, and its unit is what? Newton per what? Meter. Newton per what? Meter. M is what? The mass of that substance or of that object. V is the velocity of that object. Yx is the distance or the extension that is what? That is observed. The observed extension. So let's look at one or two questions under this to see how we evaluate the work done in a given string. Let's look at this question. A particle of mass 40 grams slides on horizontal frictionless table with a speed of 0.1 meter per second. It is brought to rest by compressing a spring to its path. By how much is the spring compressed if the force constant is 5 grams per meter? 5 grams per meter. So the first thing we need to do here is to write out our what parameters based on the given question. We have that the mass of that particle is 40 grams. Don't forget the standard unit of measuring mass is what? Is kilogram. So convert this 40 grams to kilogram by dividing by what? 1000. So if you do that, we are going to have 0.04 kg. So that is the mass of that object. Looking at the object of the question again, we are given the speed to be the velocity to be 0.1 meter per watt seconds. 0.1 meter per watt seconds. By how much is the what? Is the spring compressed? We are looking for the what? For the compression or the extension. We are looking for the what? Extension. S is unknown. By how much is the spring compressed? If the force constant, that is K. Now I told you either we call K the force constant or the spring constant or string constant. They mean the same thing. If the force constant is 5 grams per meter. Also, we have to what? Convert the spring constant to its standard unit. K is supposed to be in Newton per watt meter. From F equals what? Ks. This is our Hooke's law. K is going to be what? The force over what? The extension, which is Newton per meter. That is the standard unit of K. K should be measured in what? Newton per meter, not gram per watt meter. So how do we convert gram per meter to Newton per watt meter? The first thing, convert this gram to what? Kilogram. When we convert the gram to kilogram, then we now convert it to what? To Newton. By multiplying by what? By acceleration due to what? Gravity. Converting this 5 to kilogram, we are going to have 5 divided by what? 1000. This will give what? 0.005. 0.005 in what? In kilogram. 0.005 in what? In kilogram per watt meter. So when you multiply this result by the acceleration due to gravity, which is what? G. That is, multiply this result by 10, which should now be what? In Newton. We are going to have 0.05 in newtons per meter. 0.05 newtons per watt meter. And that is the value of the what? Of the spring constant K. 0.05 newtons per watt meter. So after getting this, let's use our formula that says that what? The work done is defined as half Ks squared, which is defined as what? Half mv squared. From this result, you can see that what? Half can cancel half. Half can cancel half. That is gone. So we are left with what? Ks squared on the left hand side, and on the right hand side, we are left with what? Mv squared. Since I'm looking for what? S. This implies that S squared will be equal to mv squared over k. Mv squared over what? K. So that ordinary S, the compression I'm looking for, will now be equal to the square root of mv squared over what? K. Square root of mv squared over what? K. Our m is the mass, which is what? 0.04 kilogram. Our v is the velocity, 0.01, over our k is the what? The spring constant or the force constant, which is 0.05. So we do that. If you apply all that, we are going to have the value of x. We are going to have the value of x to be equal to, so let's punch that in our calculator. Our mass is 0.04. Our v is what? 0.1 square dV, then the result divided by the value of K, which is 0.05. So we have what? 8 exponent minus 3. So when you find the square root of 8 exponent minus 3, we are going to have 0.089. We are going to have 0.089. 0.089 in what? Meters. So that is the what? The compression that is experienced. So the compression experienced is 0.089 meters. So this is how we solve questions that is relating to what? To the work done in springs or strings.